Alright, this is our new unit of momentum. Momentum starts off nice and easy. It's just the mass of an object multiplied by its velocity. So let's say I just have a mass that's 10 kilograms and it's rolling along at 30 meters per second. Here I would just multiply those two, 10 times 30, and I get 300 kilometers per second. The only uncool thing about momentum is it doesn't have its own units. You can call them kigums, kilogram meters per second. You could even say momentums. In terms of more complex problems down the road, we're just going to keep writing kilogram meters per second just so all our units cancel out in the end. All right, first law of momentum is conservation of momentum. Whatever the momentum before has to equal the momentum after. What's that crazy P? That's actually momentum. Physics ran out of letters a long time ago, so it's the Greek symbol rho, which is going to stand for momentum. So momentum before equals the momentum after. So if I have a ball that has 2 mass units and another ball that's 4 mass units, if this ball is traveling at 8 meters per second and runs into this guy who's stationary, if I know the velocity of one after, I can solve for the velocity of the other. Well, first I have to solve for the total momentum before. So here 8 times 2 gives me the product of 16 kilogram meters per second, and here 4 times 0 equals nothing. So 16 plus 0 equals 16 kilogram meters per second. So that means that my final momentum also has to be this 16 kilogram meters per second. So let's say afterwards, the second ball that had a mass of 2, after he collided with it, now he's only going at 4 meters per second initially. So over here I started with 16, which had to be my total momentum afterwards. And here I'm using up 4 times 2. It's going to be 8 of my momentums. So that means my other object has to have a velocity equal to that. So here I'm going to subtract the 8 is equal to 4v. And then we can say 8 divided by 4 is equal to v. So this ball, which has a mass of 4, would only be traveling at 2 meters per second. Well, hey, this guy's traveling faster, so when they bump into him, yeah, he will again, but then that'll be a whole other problem to solve. But the idea is conservation of momentum. Well, let's look at another type of problem. Same ideas. Now we're going to take rail cars. So here, this initial rail car has a mass of 20 and is traveling at 3 meters per second, and he's going to collide with this rail car that's only traveling at 1 meters per second. Now this time they're going to collide and stick together. So when they stick together, I take the total mass. But first I have to find out my initial momentum. So here 3 times 20 equals 60. And this is 1 times 10 equals 10. Now, since they're both going in the same direction, I'm going to add both of these momentums together. So 60 plus 10 equals 70. So that is my net momentum, is 70 kilogram meters per second, kgm over s. Now, afterwards, I have to find the velocity. Since momentum equals mass times velocity, velocity is going to equal momentum divided by mass. Since we already solved for the momentum of 70 kilogram meters per second, momentum before equals the momentum after. So I divide by 30 kilograms. Look at that. Kilograms cancel out in terms of my units. So 70 divided by 30 is going to be an answer of 2.33 meters per second. It's going to be my final velocity. Alright, last problem. What if they're going in opposite directions? Same idea. Here with my rail cars. This one's traveling at 1, has a mass of 20, mass of 10, but traveling at 4 meters per second. Now, because these are going in opposite directions, here when I find the momentums, since they're going in opposite directions, velocity is a vector quantity, so it matters which way it's going. So here, it's going to be 40 minus 20. It doesn't really matter which one you subtract from the other. Here, if we were going left to right, it would be 20 minus 40, and you would get a negative number, which would just mean you're moving to the left. If you keep in mind which direction you're going, it doesn't really matter which one you subtract first. So here, my net momentum is going to be 20 kilogram meters per second. Likewise, these two are going to combine. So now it's one big rail car of 30. Once again, velocity equals momentum divided by mass. So 20 divided by 30 is going to be an answer of 0.66. So here it matters which way I'm pointing in. And we're going to say 0.66 meters per second. All right, that's our first momentum. Whew, that was a long one.